Right, so I'm going to start. Good afternoon. My name is Simon Davidman. I'm coming to talk a little bit about RISC-V, simulation, testing, and obviously compliance, which is on there. It's a presentation by me, but actually most of the work's been done by my colleague Lee Moore, who's there. So if there's any questions, I'll probably butt them over to Lee. So thanks very much for that. So what I'm going to talk a little bit about compliance, why I think it's important, why a lot of people think it's important. Then talk a little bit about Empirus and what it is that we do and how we relate to this. Talk about the work that we've been involved in the RISC-V Foundation's compliance suite, and then a little bit about the experience that we've had in testing different people's designs, RTL and things like that, and then just wrap it up at the end. So first thing, talking about compliance. So question, what is compliance? And really it's about checking that a device or a technology or a simulator or whatever works within the envelope of the specification. So it's to check that whatever it is meets the specification. And is there a process or path that we can follow? Is there an established, a normal way of doing this? And actually there isn't. We're actually, there are many proprietary ISAs, there's many companies that have this, and all of them have a very good process in ensuring that what they ship out the door actually works. But the challenge that we have in the RISC-V community is that everybody can design this. There isn't one central piece of RTL that has to be validated. So even though ARM and MIPS and everybody has a very good process, there isn't an established way of getting sort of compliance for an industry where there's a collection of people working on it. So it's an extremely hard process, and the challenge is that there isn't an established way to do it in the way that we need to do it. So it's, we're on our own with this. And the challenge is that if we actually build devices that aren't complying, people aren't going to get the benefits that they're hoping to use the tools and cross-compilers and things like that. Because there's a lot of work being done in the software tool ecosystem. And the whole idea of going to a standard is that you can make use of that. And the great thing about RISC-V is you can extend it, but you still want to make use of the ecosystem as it builds. And if people build things that aren't compliant to the standard, it makes it very difficult. Obviously, if you're building a product that only you're going to use and program, it's fine. But if you're trying to build a device that other people are going to use and try and use other tools or other software, then you have a real challenge if devices aren't compliant. And that's one of the biggest problems. And of course, if you build something that's not compliant, it's actually not a RISC-V processor. And that's what the foundation says. There are sort of 3 requirements. You have to be a member, you've got to be paid up, it's got to be a working technology, and it has to meet the tests. And then you can actually say that it's RISC-V. So if it doesn't meet the compliance test, it's actually not RISC-V. It's a processor, it's based on RISC-V maybe, but you're not going to be able to put the RISC-V logo on it. So that's a little bit about an introduction. I'm going to talk quite quickly. I've got quite a lot of things on some of the slides to come, and obviously you can watch the video, see the slides after if you want to go through the detail, or maybe if my English is English and you don't understand some of the words, you can pick them up later. Empirus background. So actually, I think it's on one of these slides. So first thing is, if you think about silicon and semiconductors and EDA and the technology, nobody builds a chip without simulating it. And when we started Empirus, we realized that software was becoming more and more complex, embedded software, and we believe that no one should build a embedded software without simulating it. And actually, the challenge in the software world is much worse than the HDL world, because when you sign off a chip and you ship it out, you stop simulating, you stop working on it once you've committed. You might have to fix it later. But in the software world, you tend to ship it when it's almost ready, you fix bugs, you iterate, you deploy it many times, and actually you might have several streams of software, version A, version B, version C, that you have customers using. So you have to actually be having lots of different streams of software, and that's where simulation can be invaluable. So we think the more embedded software, the more simulation is needed. And that's where we are as a company. We founded some 10 years ago. We're self-funded, profitable, cash flow positive. Our engineering and development is paid by customers commercially using our technology. And our focus is simulators and tools. And we are sort of generic. We're not just a RISC-V solution. We're generic in that we have solutions for many different technologies. In the middle bullet there, we have simulation technology which goes across almost all of the ISAs that are public and many proprietary ones. So we have all the ARM models, all the MIPS models, Renesas, Power, ARC, all of them. So we've got a lot of experience in building models, and RISC-V is just another technology on top of that. We also have a whole load of behavioral components, so you can build platforms, boot full operating systems and things like that on it. And they don't need to be just a single core or a homogeneous core. They can be completely heterogeneous environments, because a lot of people will use a big application processor and then smaller customized processors around it. And that's the type of technology that our customers are using. We simulate that. And our staff come from a variety of backgrounds, from CPU design, CPU companies, but mainly from hardware description language technologies, verification, simulation, synthesis side of that, on the hardware side of things. And we've actually been involved with the development of several standards. For example, Verilog and System Verilog. We were involved in the development and standardization of that. So we know about the process of building standards in committees, but actually testing them and getting things compliant as well. And not only do we do simulation, we actually have a full tool suite which allows you to add custom instructions and things like that, modeling the components and doing analysis on them. So we're a simulation company with a lot of different technologies. We started getting involved with RISC-V. I went to a presentation in DAC, Design Automation Conference, in June of 16. I saw Krista present, and I went and chatted to him afterwards, and I was sort of interested. It was early, and I wrote one word in my book afterwards, which was academic, because at that point it very much was an academic thing, trying to go out to market. But actually, pretty soon customers were starting to ask us about what can we do with RISC-V and things like that. So we got interest. We joined the foundation. We're involved with several groups, the formal group, the vector group, the compliance group from a technology point of view. We've released models. We've got technology and platforms working. Our simulators and tools have been accepted. Andy's used us as a reference. They've certified our simulator there. And in the non-RISC-V, we have architecture licensees of ARM using us. We have MIPS actually using us internally and externally. So we're a sophisticated simulation technology, but we've brought out a product offering which is around the RISC-V world and brought commercial tools there. And one of the things I'm going to talk about a bit here is what we're doing with Compliance Group. And in October, we made a simulator available for free, which allows people to develop tests and quite easily. And it's a very sophisticated tool which does the whole envelope of RISC-V. So let's switch from Empirus, talk a little bit about the RISC-V Foundation and what we've been doing in the Compliance Group. Short history of that. It started a couple of years ago, and its focus is not design verification. It's not trying to prove that the RTL is going to work functionally correct and everything like that. It's to check that the design you have meets the standard. You've implemented the instructions. You've implemented the registers, and it sort of works. And common software should work across it is the idea. And so it's not design verification. We expect there to be lots of companies building solutions in their own and commercial and open source solutions to help with the verification. But the Compliance Group is focused on trying to build a suite of tests which allow you to say, am I meeting the specification? Not have I functionally implemented it correctly. And the second bullet there is that there was an agreement made about a year ago of how these tests should look. And the main bullet is really that the test should create a signature, and it's the signature that you compare. So you could run it on a simulator, you could run it in an FPGA, you could run it in RTL simulators, you could run it in silicon, and get that signature out. And if you compare the signature, then you know that you're passing the test. And back in January this year, Codicip developed or made available the first suite of tests for the 32i. We got involved as Empirus after Barcelona because Alan, who's the chairman, wanted volunteers to actually do some work. So we got volunteered to do that with another company. And in October, we released several other tests that we'd been done and made them available on the GitHub, where we enhanced the coverage and stuff. So it's a work in progress. We expect it to change. As the standards change, things will have to change. I mean, there's talk of moving some of the CSRs out of the user spec, and so they're no longer 32i and stuff like that. And that's the standardization that's going on at the moment with the 2.3 user spec. And so that will make some changes. So it's very much a work in progress. There are two components in the work. One is the actual test suites themselves, which is the assembler code that actually runs, compiles to an ELF and produces the signature. And then there's the framework that hangs that together, which runs the test, gets the results, does the differencing of it, so you can see whether things pass. And the idea is that you can encapsulate your own targets. And we include a simulator to generate the signatures. We're trying to provide examples for encapsulating, Verilator examples and commercial RTL simulators. And actually, I must apologize if there's anybody who's involved in the soft core competition that we didn't get that early enough because we were hoping that we could show how you could run this stuff on Verilator before they got started on that competition. But actually, the competition's finished and we still haven't put that up there because it's almost available. It's just not up on GitHub. So they had to do a lot of it themselves. So they had quite a few hills to climb in getting that soft core stuff to work. So the framework's there, the test suites are there, and it is available. Download, you can use it today. In terms of the test suite, I thought it might be interesting just to have a look at one. This is the simple 32i. This is a list of the instructions from the, what's it called, the RISC-V green card, listing the instructions. So there's actually 54 different assembler files that generate ELFs in that test suite, about 150 instructions each. And you can see that we've noted there some what we call decode coverage. We internally in Pieris, we're very interested in how good the quality of tests are compared to the design. And we have stuff for coverage and stuff like that. But in terms of a compliance suite, you don't really want to look at model coverage or functional coverage. You want to see how much of the architecture is sort of explored. And what the decode coverage does, it looks at the bits of the instructions and just monitors, have they been toggled legally by the tests. And we have a fault simulator that actually helps us measure this. And you can see there that most of the instructions get 100%. That means every bit the tests have been toggled and detected the fact that if they hadn't been implemented correctly, then the test would fail effectively if it didn't provide the right behavior. And you can see on the top right, a few of the branch instructions still need a few more tests because obviously some of the branches haven't gone far enough away or whatever in the tests. A few of the others need investigating too, and actually in the change to 2.3, several of the instructions have actually been moved out of the basic 32i into one with a Z in the front of it. So that we'll have to change that. And so what we do is when we've got a test suite there, we run it through our fault simulator, and this one ran 500,000 simulations in about 5 minutes on our machine. So it's running the test many times as it basically mutates all the bits that are in there. And yeah, just to cover that a little bit. So the idea of this coverage tool is what it does is it mutates legal bits. So it looks at the decode. Some bits are fixed, some bits are allowed to be switched, and it switches them, runs the simulation, compares the signature, and see if it detects a failure in there. And so it's sort of stimulating and observing. So it's seeing how good the test is in exploring it. It's looking at the metrics of the decode, but also it does do some other coverage as well in there, which we find. So it's a tool that we use and some of our customers use because it's actually very useful because you don't have to do anything but run existing tests to use it. So if you've got custom instructions, it actually tells you how much of the custom instruction space that you've actually tested and explored as well, which is good. The current status of the test suite, and this is just a screenshot of the GitHub, just for the simple ones. You know, the RV32i's got some tests, and as I showed you the coverage there. The 32IM for the multiply divide has some tests that builds on the I tests, and the coverage there is actually 100% decode coverage for that, which is good. The C is less well covered, and then the 64 bits are just starting. There are actually something like 12 suites up there to cover different things, but they're in early stages. These top three work robustly, I think, that people have used, and actually the soft core competition had to pass the top one, which is interesting, which they did. But there's a lot of challenges in doing this, writing these tests, and within the committee we've had a lot of discussion of how we should be doing it and how it should be done. But the key thing is you have to do it very carefully and monitor, watch what you're doing very carefully, and white box, walk through every instruction, and to explore what happens when it works and when it doesn't. And one of the challenges you need is really a good simulator to do that, because you have to have the whole specification there. It needs to be configurable so you can choose the right specifications. It needs to give you good messages. For example, if you use an M instruction, you're only targeting an I target, it should tell you why and stuff like that. You need all the tracing and things like that. So there needed to be a good simulator in there. And what we did is we took one of our simulation technologies, OVPsim, and built a RISC-V dedicated one of it. And we basically made it available with free, without license management and everything, as a simulator, because it models the whole envelope. So it allows you to choose which bit of the RISC-V spec you want the simulator to have, whether it's the I, the M, we do the whole of the 2.2 and 2.3 specs, and 1.10 and 1.11. There's two bits we don't do. One's the hypervisor stuff, because it's not stable, and the other's the vector stuff, because it's not stable as well. So in time, those will come. It is a commercial tool originally. but we make it free on GitHub, so you just download it, and it works Linux and Windows straight out of the box, and it runs. We also provide the full model source, so you can explore that and see what's there of the full model under Apache. And if you want to see this in operation, and rather than just use it, there's a video link, so when you come to this later, you can have a look at that. I don't expect you to write it down now. But there's still several issues that need resolving that aren't, as I said, it is a work in progress. We don't have detailed specifications of exactly how the framework should look. It's evolving as people start to use it. There's more input and more feedback on that. We've got a good indication of how we think the test should be written, but actually the change from 2.2 to 2.3 and some of the CSRs going out probably means some of the preambles that are in the test have to change a little bit. And we don't have a way of mapping the test back to bits of the specification, which would have been a good idea in there. And there isn't a formal process to say, you know, how do you rubber stamp it? What is the process? Is it self-certifying? Should there be something sent to somebody? Should there be a report that the test suite writes out and you have to send out? So there's still some work to be done. It is a work in progress, but it's a sort of collaborative work done through the group. If you're members of the foundation, you should absolutely get involved in this because it is an essential part of this industry, I think, of this. In terms of finding out who's using this, it's actually, because you just click on the download, it's very hard to see who's doing what with it. There's two notions in GitHub. One's cloner, where you just clone something and you take a copy of it. And then there's forking, where you take a copy in a structure almost with the intention to keep it in that structure and edit it and put things back. And there have been 46 unique cloners and 23 forks in there. But you can't really tell who's doing them. But you know, from questions that have been asked and issues on the GitHub or through the groups or to emails with us, there's quite a few people starting to use it, who've putting their processes through it. We know of several successes that have gone through, which is good. And obviously the softcore competitors had to use this. And you know, if you are starting to use it, there's issues. Put issues on the GitHub, and we'll get to them. We want to try and understand what's going on. And just an example of usage. So this is one, a company, Valtrix, out of India, that basically started using this format of running the test with like the compliance suite with the signature, everything like that. And they've sort of evolved it so it's actually a test generator. So it can use directed tests like the compliance suite, or it can actually create tests, and actually what they do is they wrap it up so they can put it in the target directly, so they sort of wrapped it up so you can run inside a simulator or an FPGA or an RTL simulator or silicon, which is a very good way. And they're using the same simulation technology that we're using as well in there. And so this is an extension of the work that people are doing in compliance, but it's the same sort of methodology of a signature and everything, which I think is very good. And we'd expect to see, with more and more people needing verification of RISC-V, we'd expect to see a lot more of these types of technologies using this stuff. So a little bit about compliance experience here. So what we've been doing is we've been exploring people's designs, and this is our experience. It's not a discussion of what our customers do with the tools. It's what we've been doing with customers for partners, actually for fun, when we're sort of curious about things. And we've looked at proprietary RTL people have sent us, open source RTL, FPGAs, silicon, simulators. We've looked at everything. And the goal, what we've been doing is basically just looking. We run the ELF files, we write a signature, and compare it. So we're doing effectively exactly the same as the compliance suite does. We've had to develop this encapsulation, and there's several different, whether it's hardware, where we're talking through a GDB server, or whether it's an FPGA, or whether it's a simulator. There's different approaches. And the idea is we're learning about this so that we can try and put this knowledge into the framework of the compliance suite to make it easy for people to have something to copy as they want to try and run things. We also have not just the compliance suite, which is something we're sort of donating and working on. We have a huge internal test suite and a methodology that we built over the last 10 years of all the technologies that we've been working with the other vendors. Because, you know, to get something like an 8-core ARM system running, you know, Linux, SMP Linux is pretty hairy when it's got very complex things, and we do it very clean room. So we've learned a methodology of how you build a complex model with a sophisticated testing all the way. And one of the things that's interesting is there's a lot of talk about compliance of the instructions of RISC-V, but actually we see that in the real world, most of the issues are all to do with what's called the sort of privilege. It's not actually the basic instructions. It's the complexity of how things interact, how different cores interact, and it's the sort of the system issues, not the user stuff. we don't just build simulators, we actually have a whole bunch of other technologies for source code for the model, instruction coverage, the fault simulation, decode coverage stuff, and a methodology that works all with custom instructions. So there's a lot more to it. But what did we find with these different things? Well, I'm not going to say specific things about specific things, but we found missing registers, where they hadn't implemented the register, which are mandated, missing instructions. Oh, I didn't need that instruction, so I didn't implement it, which is fine for them, but useless if they're trying to be compliant. We found issues were quite interesting in the floating point in some of them, where they were switching modes in a way which actually wasn't defined in the specification. So some of that is actually questionable clarity in the specification, and we found issues with the memory protection units, which actually were catastrophic in one case. So several different issues, which we reported to the people that we've talked to, just to sort of help out there. And so in terms of running compliance yourself, yes, you can just download it, as I said. You have to work out how to encapsulate your target. And the idea is we're trying to do it so there is an example which works with commercial simulators, with Verilator, with the, so that and with the GDB servers, another one we want to try and do. To try and help you make it easy for you to run yours on it, I would suggest you start with the 32i test, because that is very comprehensive. And also it's mandatory. Yeah, everybody has to do 32i. It's not an optional part of the spec. And then when you change your design, you should be running it in your regression suite, and you should keep an eye on the GitHub repository, because when we make changes, you should really update and use it, and check that your stuff's still running. So in summary, just to wrap up, so it is a work in progress. The framework as it is now on GitHub can be downloaded and used now, and people are finding it useful and finding bugs, and I think it's great when they come back and say, "Yeah, we found this bug or that bug," and it's very interesting. They often find bugs in the tests as well, and in the compliance suite, and we fix those as well. But so it's good. Yeah, we've started on the 32 ones. We've still got some work to do. We have examples of these already running, but the coverage is pretty poor. We ported the Andrew Waterman's RISC-V tests, the test suite, and one of them gets like 30% of the decodes done. So it's pretty primitive, and so there's still quite a lot of work for that stuff. But the great thing is we're starting to understand what the issues are and the requirements are, and people need to really internalize it and make it a fundamental part of their approach. This as part of verification, but in this instance you have to worry about compliance, because if you license a core from ARM or somebody like that, they've done 100% of the verification, and you just need to do a little bit of it. Whereas in this case, you have to worry about all this yourself. So it's a different challenge here. So how do we help? We're a commercial company. We provide some stuff for free, but we actually sell solutions to help people. We've done a lot around the RISC-V stuff. We have models also of these specific cores from specific people. We're adding to that. We have platforms which run FreeRTOS on a microsemi and things like that. And we have all the tools as well. And it's not just RISC-V. We're very heterogeneous. We have all these other technologies that we've learnt on, so we can apply that to RISC-V, which I think is very useful. So more information. We have two websites. We have Empirus, which is our commercial stuff. We also have ovpworld.org, which is the standard way that we model platforms, which is an open standard way of modeling platforms, behavioral components, CPUs. And actually, that's where all the models are as open source under Apache and stuff like that. And then obviously there's the RISC-V compliance. And if you want more information, there's my email and Lee's email. So with that, I'm done.